This seems to be working, I hope. Sounds good. So this is actually my last lecture, which is good. I thought I needed to say two things before starting in earnest. The first thing I want to say is thank you very much for the note takers. Could you guys lift your hands? Kind of, hello, hello, hello. Great. Thanks so much. I hope I'm not too much of a trouble for you guys. Please ask questions if you have them. And the other thing I wanted to say before starting is thank you for my co-lecturers, Brigitte and Anya, for doing all the hard lifting of this stuff. So, I can talk about the fun bits and comparing systems and stuff like that, while they actually do the hard actual work of proving things. So, yesterday I talked to you several times about the fact that you could consider terms in the Lambda-Calculus as proofs in modal logic, and today Brigitte proved 3 theorems, right? She proved one theorem which was just box A implies A, and I think it's still there. She proved that box A proves box A, which is the form in modal logic, somewhere over there. And then she proved another theorem that I didn't understand much because I was in the back and I couldn't hear very well. But she also said that her slogan was that one there, that truth is living in the moment, here and now, and validity is living forever and everywhere. And if you remember, one of the things that I said was that maybe we don't want to have a very, and this is a great semantics, right? This is really very clear and very compelling, but maybe you want to have different ways of thinking, and you don't want to be so tied up to a particular way of thinking about things. And maybe you want to have different kinds of boxes and different kinds of diamonds. But we certainly agree, Brigitte and I, that you should actually have more than closed terms, that you should have a collection of variables giving you a term, and this is kind of where so the systems that we have are very similar. When push comes to shove, you can just prove equivalence between them. So that is just connecting to yesterday and to what happened this morning. And today I'm going to do something very different, because we kind of we did overviews of Curry-Howard in general, and I tried to show you several different places where Curry-Howard can be seen at work. And then I talked about specifically linear logic and specifically modal logic. But today I want to do something, I want a story that's much more specific. And it's another old story, and I feel a little bit more worried about telling you this story, because I think the previous 2 stories, you might agree with me or not, you might not like my version of the story, but it's important for you guys to know about these stories, because they are kind of essential to the kind of stuff that we do. But the story that I'm telling today, it's not on the same level of importance or kind of, I don't guarantee it so much. But I want to talk to you about linear functional programming and a specific kind of tool for linear functional programming. And as usual, I started with the history of the stuff, because this stuff started in kind of late 90s when Ike Ritter did a PhD in Cambridge on categorical combinators for the calculus of constructions, so in 1992. And I did my PhD, which was on the dialectic categories, which I mentioned briefly, but I'm not going to talk about them today. And they turned out to be models, categorical models of linear logic. And we should kind of sat together and try to kind of put the kind of work that we did for our PhDs together, and came up with this idea of categorical abstract machines for linear functional programming. And that was a project paid by the UK NSF called XLAM, so for X for explicit, and then S for substitutions for linear abstract machines. And this is very different from the stuff that we were discussing yesterday and the day before, but it has several similarities too. So the point of it is to do what I kind of keep trying to point you to, which is this idea that category theory kind of shows you some deep structure in syntax. And that is a phrase of Martin Hyland, who was my supervisor, and I showed you a picture of him before. So that's what we're doing today. And you know, if we finish earlier, so much the better. We don't want to have roller coasters every day. It's too tiring. So what happened with this project XLAM? It was more than 25 years later, so I feel a little bit worried about talking about things that old in an audience with many computer scientists. But we had lots of conference papers. We had 2 journal papers. We had a master's thesis, 2 international workshops, and 1 that's a meeting out of this work, and also lots of publications and stuff like that. But there's I keep telling you sayings of that I heard. So there's this saying that it takes 20 years for work in theory to make its way into practice. So in 2016, some of this work that we did on linear logic seemed as if it was coming to fruition or kind of being applied for real. And you guys must have seen that in 2018, the guys got linear types accepted into Haskell. So we have linear types in Haskell. It took according to one of the main developers, it took 4 years to actually, from acceptance to trying to do it to doing it, took 4 years. And one of my reasons for trying to talk to you about it today is see if by any chance it's time to try it again. And since then, there's another 5 years gone by, right? Because it was merged in the REPL in June 2020. So, the situation as it stands at the moment, I think, still is that despite the obvious promise and a huge research literature, the linear types have not made into mainstream programming language. And even though linearity itself has inspired uniqueness, typing clean, ownership typing Rust, separation logic, and lots of other interesting kind of work, we don't have, we have linear types in Haskell, but we don't have a very compelling use of them quite yet, as far as I know. I love to hear the CEO's tweet talking about it, because it always makes me feel confident that it's just around the corner. But I don't think we have it quite yet. And so, one tool that I think people have not used as much as they could, and I would like to try to sell it to you, is this tool called explicit substitutions. We've heard lots about how substitution is difficult and it's a problem, and actually even the guy who invented the Lambda-Calculi first had an inconsistent system because he got substitution wrong. And what I kind of wanted to talk to you about is this idea that, it's not my idea, I'm going to show you in a minute the guys who did it, but it's this idea that one should kind of, instead of having substitution as an implicit operation happening on the meta level, you should make them part of your calculus. So, so this is a bit of Wikipedia. In computer science, Lambda-Calculi are said to have explicit substitutions if they pay special attention to the formalization of the process of substitution. And this is in contrast to the standard lambda calculus, where substitutions are performed by beta reductions in an implicit manner, which is not expressed within the calculus. And there is a huge literature on explicit substitutions, lots of different systems, again with a difficult, it's difficult to situate yourself because the systems don't normally explain how they compare too much to others. But most of the systems, just a second, have no models. And the system that I'm going to talk to you about today has categorical models. Yes, please.
So by the fact that they have syntax but no models, is that sort of meaning they have syntax but no semantics? Or do you mean they have syntax but they don't have a mapping to category theory in the correspondence?
They don't have semantics at all because they don't think they need it, right? You know, they think the semantics is just what the machine does. It's the rewriting that happens with this particular calculi. At least that's my understanding. I'm not an expert on that, but I still want to show you the system that has models. Right. So. This is a little bit from the guys who actually invented, or my understanding is that explicit substitutions is an implementational trick that was made into theory by Abadi, Cardelli, Curian, and Levy in 1989. And what they say is this business that substitution is the eminence grise of the lambda calculus, which means, the guy behind the scenes kind of manipulating everything. In classical beta rule, which everyone knows what it looks like and everyone's seen it more than twice recently, you use substitution crucially through informally. And here A and B denote terms, and A with B substituted by X represents the term A where all three occurrences of X are replaced by B. And the correspondence between the theory and its implementation becomes highly non-trivial, and the correctness of the implementations can be compromised. So what I'm trying to sell you is this idea that if you make the calculus more explicit about the substitutions, then proving the correctness of whatever you're implementing is going to be easier. It's not easy ever, but it's going to be easier because you're making the things more similar. So, so these are the guys, Martin Abadi, Luca Cardelli, Pierre-Louis Curian, and Jean-Jacques Levy, and that's the paper. And, it's old, it's, as I was saying, it's very old, but it's still extremely cited. So it has more than 1,200 citations, and even this year it has more than 20. So it's still kind of very much, and it's called Lambda Sigma. And most of these guys have changed into different things. They haven't carried on working on that. They kind of produced this stuff and stopped, as far as I know, thinking about it. And I mean, you're going to say, well, Valeria, why are you kind of bringing this stuff in now? And I kind of want to say that, once again, what I want to do is connect that to the Curry-Howard correspondence. And why do I say that? Well, I say that any syntactic calculus that is well-behaved, and lambda sigma is well-behaved, should have a categorical semantics. And I want to use mathematics as a source of intuitions. And I explained that that means that the implementation, it's not exactly proved by construction, but it's more proved by construction than if you hadn't tried to have the semantics in place. And we discussed that yesterday and the day before for both propositional propositional logic, intuitionistic, linear logic, CS4 with box and diamonds, and others that I just passed quickly under your eyes. But I say that we shouldn't have it for lambda sigma too. So, before kind of starting on that, I wanted to repeat obvious things that everyone here should know, right? Why do we care about functional language? Well, we care because we think that we want programs to be as much as possible like mathematical functions, where you can reason about them by transforming inputs into outputs and knowing how they will behave. We kind of think that because they work on inductively defined data structures and they have no side effects, then we can employ mathematical reasoning and lots of times substitute equals for equals. And I think everyone here, I hope, believes this business that function definition and application is the central part of lots of the language that we care about, like Haskell, or Camel, KML, Rust, Scala. So we want to use as much as possible our possibilities of type checking to detect as many errors as possible at compile time. So it's so obvious, it's all something that you all know, but it might as well repeat it to remind ourselves of why we bother. I'm not going to go over the things that I'm not going to talk about, because it's silly. So let's kind of start describing this calculus, this lambda sigma calculus. So first, we have to start with the lambda calculus itself, which you've seen several times, but I'm just going to present it again, just to say that in my books, normally you have to have some ground types, and since I'm talking about the simplified lambda calculus, not the dependent one, I just have one term constructor. And again, I could have conjunctions and disjunctions, but I just have the implication, which is the arrow type, and I have the normal terms for type terms. And of course, variables are placeholders. Lambda x of type A applied to term n is a function expecting an input of type A, and n applied to n is just function application. And of course, the simplified lambda calculus singled out well-formed terms and checks whether the correct kind of argument is supplied. And these are our normal rules, so there's nothing much more to say about them. But also, you know, we know that what we can do with that is mostly computation via beta reduction, where you substitute things, as we're saying, at interval. Now, I'm told, and you know, as I told you several times, I'm not a proper computer scientist, I'm not a mathematician, but I'm told that implementing beta reduction efficiently is very hard, and that the traditional solution is to reduce lambda terms in an environment, storing bindings for terms for variables separately. And that one has two kinds of expressions. The environments that are lists of bindings, and terms that were like the terms that we saw in the previous slide, but plus closures, which I'm going to write as F star n. And this F is going to be a collection of bindings, a list of bindings. So the modified beta reduction that apparently people have stores the substitutions in the environment, and we have to produce a collection of rewrite rules that eliminate the substitutions that we are putting into the environment. And the name of the game here, I mean, yesterday when I was talking about, or the day before, when I was talking about making categorical models of type theories, I was saying that the name of the game was to find the appropriate structure for the different constructors of your type theory. Here, we're talking about a different game. The name of the game here is to decide what are the best rewrite rules that we can put in a system like that, so that we have the best properties that we have, that we can have for our system. And as I was saying, we want to transform this trick of implementation that people have done quite a few decades before the 1990s, when Abadi et al. Came up with the calculus, but we want to transform this in some sort of theory. So this is the reason why they came up with substitutions. Go ahead.
So this means that when we evaluate lambda x dot t applied to you, we don't just get a result, we also get the bindings.
We have the bindings separate, we have our context of the values that are associated with the variables, and you kind of have sideways this collection of lists and the description of how we're going to rewrite this thing. So these are the abstract machines that we want to have different versions for. And because we are very ambitious, we want to do that for different logics as well, right? One of the things that I already mentioned at the beginning, and that is that actually the person who first started thinking along those lines, Dr. Ritter, actually did that for his PhD for the calculus of constructions, so for dependent types. And I don't think he had universes, but the more complicated version. Okay, so I'm not going to give you a complete description of the lambda sigma calculus, but I want to have a discussion of the key ideas. So, the main basic stuff is that we're going to have funny kinds of judgments, like the one on top there, that gamma proves an F delta. And that's not like we normally have been reading our judgments. I don't mean that F is a term of type delta. I mean that that's a collection of substitutions, right? It's a collection of things that need to be substituted for other things that I'm storing on the side, as we discussed a minute ago. And one of the other basic ideas is that, there shouldn't be anything, we're inventing this extra category of judgments and this extra kind of entities that are the environments and trying to make them part of the calculus, part of the type theory. But these guys, they don't have a logical role to play, right? They're just helping us do the substitutions so that we don't get into the issues that Church had and that lots of other people had when implementing things. So in some ways, every lambda sigma term has to be equivalent to a proper lambda term. And one of the points that's kind of difficult for mathematicians when they look at this is to say, okay, then the context, the variable z of type A product B, this is not exactly the same as x of type A and y of type B. They have to have a relation, but they're not exactly the same. Right. So, now, think with me. We want to have this collection of substitutions, and substitutions are a little bit like permutations, right? So if I substitute an x for a y, and then a y for a z, well, it's got to be the same as substituting the x for the z. They compose naturally. And that is the last rule here. So I have an f that kind of mixes up the gammas into deltas, and then a g that takes the deltas into size. So I need to compose them. I need to kind of apply the substitutions, right? I invented them so that I could apply them. So that's what the star, the closure there does. Because the second judgment here, the gamma proves T of type A, that's a decent, honest to goodness term judgment. Yes?
Yeah, the star is just a syntactic operator.
Yes, absolutely. And now I have to explain what the two top ones, because I started from the bottom, right? So the two top ones, that one here is saying, oh, I have a collection of substitutions. I can always make another parallel substitution. So that's, if gamma proves T of type A, I can always extend the substitutions of X, T for X. So I had a list, I append to the list one extra substitution. And of course, you have to start from somewhere. So you have the looks like an empty substitution, but you kind of can think of it as being the identity substitution, right? I don't do anything, and that's an empty, and you have to have some sort of, you have to remember that your logic is intuitionistic, so you can have a sub-case of the list of substitutions that you're dealing with. So these are, and of course, the difficult stuff, as I was saying earlier on, is how to evaluate the substitution. So how do you rewrite and have the best properties that you can have? So what the substitutions, explicit substitutions do then? They incorporate substitution operators into the language and transform equalities that we have from the traditional type theory into a set of rewriting rules. And you this is transforming this clever implementational trick of using environments into some sort of theory, because now you have a new type theory with extra kinds of objects, right? You have the terms that you always had, plus the substitutions, and you have ways of transforming both of them, and ways of connecting them on that rule, the star rule. Now, the composition of substitutions allows very sophisticated interactions. And there's a strong problem, a very big problem, that for many years people saw this calculus of those guys, they thought one would be able to prove strong normalization for this calculus. But Paul and Rebellier kind of came up with a famous counterexample. So we do not have a strong normalization for this calculus. And that's one of the reasons for a variety of explicit substitutions calculi, because some people think that having strong normalization is one of the essentials of life. And some people don't think so. Yes?
Is this counterexample simple enough to explain, or is it outside the scope? Or are you going to get to it?
Sorry, say it again?
Oh, I'm just curious, can you explain what the counterexample is, or is it too?
No, I'm sorry, I can't. I can say a little thing about it, which is that it is about substituting some things and then substituting back into them. So you get into a cycle that never terminates.
Okay.
But what is the exact counterexample? I'm sorry.
Okay.
I have no idea. Right. So far so good, right? We it's a bit like what I was talking about yesterday when I was saying that Adrian Emoji kind of came up with a way of thinking about non-termination of programs, and that we kind of could make category theory out of it by thinking of the way that he was thinking about this computational Lambda-Calculus as a monad, and saying, oh, that's just instantiating different monads. Here, we're doing something a bit similar. Well, those guys were doing something a bit similar, because they said, look, this is something that everyone who wants to implement Lambda-Calculus has to do. So let's kind of try to make it type theory like we know and love. So now, what we want to do now is actually kind of see what is the semantics of that? What is the categorical way of thinking about that? If you just come at it, you're not an implementer, you're just kind of being given this calculus, and you want to see, can we do something about it? So that's what we're going to do. But as I was saying, there are lots of choices. Which explicit substitution calculi, which term constructors you require. I showed you mine, because, I showed you the guys, A, C, C, L, alpha Levi, and because it was the original one, and because it's the one that I like, but there's lots of others. There's lots of different equations that people discuss. I did mention that what I want to do is to discover terms and equations for different logics, and I also mentioned that I want to use the methodology of extending Curry-Howard. So this idea of category theory as syntax debugging. And I actually kind of also want to use internal language theorems to kind of provide to prove that the constructs are sound and complete for an equation theory of them. So far, so good. That's just what I want. And the key idea is that we actually already agreed amongst us now is that these principal institutions should include the underlying lambda calculus, that there shouldn't be anything else there apart from lambda calculus, and that the context, well, they should be isomorphic, but not exactly the same. Cool. Now I have to kind of be nasty to you because I was saying to you that in the first day that you only needed to know what a category is, a functor is, and a natural transformation is, and that you just have to find the structure within this stuff, and we'll be cool. But I was lying a little bit because I actually need you to have an extra layer of category theory. I need you to have a vague notion of an index category, which is something that Anya kind of described to you on her first lecture when she drew. I hope you remember that drawing. She was saying that you have the types here, and then you have a box here, and all these guys kind of come over this type here. That's the picture that I need you to have on your heads. That there are types down here, and they are, well, you see, that's the thing. Each one of these fibers over a type is going to be a whole category. And that's what you need, both for dependent types and for this notion that I'm kind of trying to slowly build up of a model of explicit substitutions. The point, there's one point that I wanted to make here that I am forgetting, just a sec. The point is that what we have on the basis is the context that Anya and Brigitte have, right? The